The lubrication film thickness. What's so important of the lubrication film thickness? Let's start from the very first beginning. Lubrication is a machine's method of protecting its joints and ensuring that the machine as a whole is in good working order. The lubrication film creates a barrier between the softer material of the bearings and the other parts of the machine. This helps defend the bearings against the excessive wear and tear that can dramatically reduce their useful life. Back to the beginning. If we think about the reliability of a machine, that's in general referred to as asset reliability. A component of course can be a bearing. So we could say, bearing reliability, or component reliability, but the reliability of that really equals the quality of the lubrication process, or the product itself. And quality lubrication, and we talk about as a concept, the excellence of, also equals the 6 lubrication rights. These rights cover a set of questions that one would ask about any particular lubrication point in the machine. If you would answer, no, to any one of those points, then you have a problem with your lubrication reliability. The implementation of the 6 lubrication rights is really the foundation of lubrication reliability. So if you answer, yes, to all of those 6 questions, then you have a good lubrication reliability strategy in place. Lubrication reliability really covers 10 fundamental steps. 10 things that one needs to do to ensure that again we say yes to all of the 6 lubrication rights. The focus fundament, and this is the basis of the whole thing, is the storage of the lube. It's the conditioning of the lube. It's how we dispense the lube and how we monitor the process. If those steps are not in place, all of the other 6 steps in the whole 10-step fundamental process will not work. So, a little bit about facts and physics. Bearing failures. Bearings are really the heart of the rotating machine. If the bearing fails or is disturbed in performance in any way, so does your machine fail. We know from statistical analysis, and work over many years, that about 60% of bearing failures are lubrication related, and there are many things under that concept, lubrication related. The lubricant is really the lifeblood of the bearing. It reduces metal-to-metal friction, because it separates the rolling elements, or the moving components in the bearing or in a machine. And in separation, it reduces surface wears. It minimizes surface-to-surface touching, and as a result, a reduction in wear is an increase in component life. The key to the whole thing is really the lubrication film thickness. In order to have a good bearing operation, we need to separate those components with a lubricant. This is called the lubrication film thickness. And typically, it's very small. It's 1 to 3 microns. So it is critical. Clean and pure, uncontaminated lubricants are critical for this application. And this is what we're trying to do with the concept of lubrication reliability. We're trying to make sure we have a very good lubrication film thickness. By the way, did you know that 10 ppm of water in a bearing lubricant will half the bearing's lifetime? This is the relative amount of 2 drops of water in a glass of great beer. Now, let's have a look at the effect of wear, or contamination in an oil, to bearing life. Bearing contamination and its effect on life was well known back in the 80s, and a lot of work was being done then by a lot of the big companies. For instance, SKF in Sweden did a lot of research work, what they call the SKF New Life Theory. They were trying to find a way to build into the life calculation of the bearing a parameter that considered the contamination level within the lubricant. If you knew the type of contaminants and the size and amount of those contaminants, you could factor these into the equation of bearing life. It could go down or it could go up. Now ISO also got involved in this, and they started to develop a strategy, which is today known as Standard ISO 4406, where they measured the number of components in 3 different size groups. In this case 3, 5 and 15 micron in 100 milliliters of oil. And with each of those amount of quantity they are given a code. If you look at the graph, we have an ISO 4406 code of 22/18/13. Now this could be a very normal, operating contaminant level within a gearbox. And I know many new lubricants are this dirty, but if we were able to increase the cleanliness level to an ISO code 16/12/8, which by the way, would be a best practice for a hydraulic system, we're looking at a 4 times increase in life. The mean time between failures in hours would increase by a factor of 4. Another very interesting statistic is the research work done by Dr. McPherson from Westland Helicopters. Here Dr. McPherson looked at millions of cycles to fatigue failure of a bearing, and he related those to the filter rating element size, filtering the oil. So this is the particle size in micron, where the filter element was a beta 200. Bottom line to this, if you took a 40 micron filter, which I refer to as a rock catcher, you can see on the scale of infinite life, we're not going to get much life. On the other side of the scale, if we're running with a 3 micron filter element, we can have infinite life. What this is really saying is that if the bearing has a contaminant level lower than the lubrication film thickness in the bearing will not wear and has an ultimate life. Talking about film thickness. How much film thickness can we expect in different applications? It varies roughly between 0.1 and 450 microns. Most of the time, when talking about bearings and gears, we talk about a 0.1 to 5 micron range. Exceptions are journal or hydrostatic bearings. Here we are talking about a larger film thickness. To put that in perspective, how big is 0.1 to 5 microns? In this overview we are comparing various particle sizes. Human hair, for instance, is circa 80 microns, whereas white blood cells are 25 microns. Already at 40 microns, there is a limit of visibility. As you will see in the slide hereafter, the film thickness of a bearing is roughly 1/20th of a strand of hair. This means virtually invisible to the naked eye. Finally, we arrive at the point where this chapter is all about. How does wear really start? If you take this cross-section of a ball and an inner ring, you can see the load zone. This load zone is separated by the lubrication film thickness, which is very small. So small that if you pluck one piece of hair out of your head and put it under a microscope, and with surgical tools were able to cut it 20 times slice-wise, that's the thickness of the lubrication film in a bearing. So think about this: if you've got a piece of silicone sand floating around the warehouse, or the factory, or the store, and it's 20 microns in diameter, and as you have seen in the slide before, you can't see 20 microns, and that goes through the bearing, it would have the same sort of effect as if you drove your car over a rock about a meter in diameter. So this is how wear really starts.